Good evening, everyone. Good job for the most part last week. It was my mistake. I gave you a rubric that didn't include the grading of the abstract. So some of you did not give an abstract, and I only clued in when Spencer said, hey, I was a little confused. And again, it was my mistake. So if you did not include the abstract because you didn't see that I was grading it on the rubric, submit to me this week, sometimes this week before Sunday night, an abstract to go along with that, and I will up your grade, okay? There were several people who did that. All right, this week's module was supposed to be the last lab report, but considering that you guys have a staycation, I'm going easy on you, and I think I've required enough lab reports. So I'll go through the expectations. It's not a lab report. It's several questions that you'll go through, and we'll work through that. I'm hoping nobody started this module and started to write a lab report. I'm sorry if you did, but I'm thinking that nobody has started yet. All right, so I see by the poll that most of you have learned about Le Chatelier's principle. I'll go over it very briefly just to set the stage. It's a really nice virtual laboratory that explains this concept, and it gives you a visual to go along with it. Okay, just going to share my screen. Everybody can see the screen, okay? Okay. So this week's module, as usual, you have a pre-lab, and it goes over what Le Chatelier's principle is. And it's this idea that when systems are in equilibrium, they want to stay in equilibrium, but you can mess around with them or disturb them or perturb them in a number of ways that they'll get away from equilibrium. But in their minds, they want to return to equilibrium despite that disturbance. So Le Chatelier's principle is a way of predicting if a system at equilibrium is disturbed, how it will shift either to the left, to the right, or maybe no shift at all in order to regain that equilibrium. And remember, equilibrium is the rate of the forward reaction equals the rate of the back reaction. It doesn't mean that the concentrations are all the same. It does mean that the concentrations of the reactants and the products do remain the same, but they don't have to be exactly the same, if that makes any sense. Okay, they can be different concentrations, but they don't change with time. The concentrations don't change with time. Okay, that's a little bit of an overview. There is an associated quiz. So if you go into the overview, you've got an introduction to this lab, which looks at one of the transition metals called cobalt. When it reacts with certain things, it forms what we term complexes, and these complexes in aqueous solutions are different colors. So that different colored solutions, we can actually tell whether it's on one side of the equilibrium reaction or another side. More on that in a minute. But this video will describe to you exactly what you'll be looking at, these color changes, in order to denote whether it's still on the left-hand side or the right-hand side. So watch that, and then you can take that quiz. This week's module, in the lab module, will lead you to this Word document that will look something like this. So it is a clickable, interactive virtual laboratory that really emulates exactly what we would have done in person. So it's another one of those, like, it hits the mark perfectly. I have created this, and I've done a lot of screenshots just to walk you through how to navigate and click on things and actually get to the lab. And the lab, if you don't click on things like the little introductory video here, it's kind of hard to know what to do. So I really encourage you to click on that introductory lab video and support, and it walks you through just how to navigate, how to pick up a beaker, how to pour stuff into it. So the functionality of that platform that this site is on. So you'll be working in a virtual lab, and what you're going to do is you're going to bring up the instructions here. The instructions, though, if you want to read the instructions and then do the lab, it's kind of hard. You have to toggle between the two. So what I've done is I've copied and pasted that total sheet of the instructions, and here it is. So this really is the meat of the laboratory. It has the objective, a little bit on the background, which I'll cover momentarily, and then the assignment. The assignment consists of 5 steps, going through and changing some things, looking how, if you change concentration or temperature, how you shift equilibrium and how that reaction will try to get back to equilibrium. So it's perfect way of looking at Le Chatelier's principle. You get to be the perturber. You get to go in and take something that's at equilibrium, mess around with some things, and notice how it shifts. And those shifts are denoted by color changes. Okay, so 5 little things here in the assignment. For each one of these, I followed up in the post lab. So let me jump to that. And I just said that there is, take me back. There is no lab report. In lieu of a lab report, I just want you to do these things. So those 5 steps that you just saw of the assignment, I want you to work through. But for each of those steps, I want you to briefly explain what you did as if you were writing a experimental or method section. But it doesn't have to be detailed, just brief, okay? Remember to write this in the past tense. An Erlenmeyer flask was filled with cobalt chloride, period. Short sentences in the past tense. Third person, meaning there's no relation to a person doing it. It's all, it was done. So no, I poured this. Nope. The solution was poured into a beaker. So get rid of the I's and the we's. Commonly in chemistry literature, as well as biology, and even in medicine, the experimental section does not have these I's and we's. It's in the third person, passive tense, past tense. Okay, so briefly describe what you did. Summarize briefly your observations and any of the values that you collected. In some of these steps, it's asking you to collect the concentration values so that you can calculate a K value, equilibrium constant. Show your calculation of K when it asks for it. It actually asks for it in the 5 steps, each of those 5 steps, okay? And also watch that you're at a constant temperature. And I think the 2 last steps get you to change the temperature. So you might want to report the temperature of the equilibrium constant if it has changed. And then the last step is really what you would have in a discussion. You've looked at these observations, you've done the calculations. Now, what the heck do they mean? And since this is all related to Le Chatelier's principle, you're using that principle to explain it. So if we mess around, like increasing the concentration of products, for example, the system will shift back to the reactants to produce more reactants to try to diminish that increased concentration of the products. Okay, so try to relate that back to Le Chatelier's principle. That's it. And then you'll upload your questions here to these 5 steps of the assignment. Is that clear? Okay. You see my document camera? You do? You see my
Yes.
hand? Okay, thank you. I just wonder sometimes. Okay, the system at equilibrium is this, and cobalt is really neat. It comes from the transition metals, as I said, and often these transition metals, when they're in aqueous solutions, are often neatly colored. And Joseph, perfect lighting, because that's the pink that you're going to see when cobalt is connected or surrounded by these waters in a hexahydrate ion. So when it's surrounded in a complex with water here, you're going to get a pink solution. So you know that you're on the left-hand side of this equilibrium. If equilibrium is dominated by the product side or the right-hand side, I hate to call it reactants and products because they can toggle between the two. So we often say left-hand side and right-hand side. When it's dominated by more things over here, that color is going to change, and you're going to have cobalt in a different complex surrounded by chlorine. And when it's surrounded by that, it just changes its nature of interaction with light, and it actually looks to us like a blue or even purple solution. So I have my color coding nicely here so you remember that. And this is a good precursor for the quiz, which asks you some of the colors here. So you might want to jot this down. So awesome, we have a system here. If we let this system come to equilibrium, we can go in and again, mess with the system. We're going to perturb it or disturb it. And we can do it 3 ways, but we're only going to look at 2 ways in this laboratory. The 3 ways, and your instructor might have done this with you, I did it with my students today, is we can change the concentration of something. We can change the concentration either by upping it or decreasing it, and the reaction will shift based on Le Chatelier's principle. Okay, so let's take an example of that. Say the system's at equilibrium and I add more of this product or right-hand side guy, right? Add more of it. The system sees that and it's like, whoa, I've got more of this. I want to try to diminish that addition of that cobalt chloride complex by reacting it with water and forcing the reaction to go back to the left or to the reactant side. So you'll see that shift, and you'll see that shift because we can look at the color changes, right? You can add more of this and it may be shifting if you add enough, and you got to add enough sometimes to change the dynamics that are related by the equilibrium constant to get to that pink side. Okay, it's not instantaneous. You don't just add a drop of this stuff, increase the concentration, and it shifts over here. You got it, it's like a tipping point, right? It may be balanced and you got to tip it. Okay, so that's changing in concentration. If I up that, it's going to shift that. What if I remove some of the chloride ion? Remove some of the chloride ion, what's going to happen? Which way are we going to shift?
Shifts to the right.
Yep, it's going to shift to the right. Great, I'm taking that away. The system sees that. Are we going to shift to the right with removal of chloride?
Wait, removal of chloride. So it's decreasing. Wouldn't it shift to the left then?
It's going to shift to the left. Good. I bought into your first answer. I was too quick to go, it's going to shift to the right. Yeah, you're decreasing this. And look at this. Imagine this system very, very happy at equilibrium. And you come in and you take some of this away. The system says, hey, I was perfectly happy with the amount of chloride and you're taking it away. I'm going to do everything to try to replenish what you took away. Okay, so it's going to shift to the left. Think of it that way, and that always helps, right? If we add, say, this cobalt hexahydrate and we add more of it, the system's like, whoa, I was really happy with the perfect amount and you're adding more. I'm going to try to get back to that concentration. It doesn't, by the way. It gets close to it. It's going to try to get back to it by shifting this way. It's going to make more product. It sees that and like, I can make more product, and shift it away. So these things are sort of compensating. They're intercepting to diminish the impacts that you're doing upon that system. Concentration was one. I'm just going to mention this. Your instructor will mention it. It's not valid here because you have to have gas phase constituents. We're looking at aqueous phase here. Everything is in solution. But you can change the volume, and when you change the volume, you change the pressure. It's an inverse relationship here. I'm going to leave that one out. I'm going to just put yep, it's valid, but not in this experiment tonight or this week. I'm pretending that we're doing it tonight. Last thing is the changes in temperature. And this relates to whether a system is exothermic or endothermic. And you can change temperature by increasing temperature or decreasing temperature. For this, we have to know whether it is endothermic or exothermic. If something is exothermic, it gives off heat. And if this system is exothermic, if we're told that, or if we figure it out, I just like to include heat on that product side. If it's endothermic, it requires heat to go in this direction, and heat would be over here. I like to add that just like an additional product or an additional reactant if it's endothermic here, because that allows me then to figure out what's going to happen. Say I change the temperature by increasing the temperature. I'm adding heat. So I go over here and I jack up the temperature. Again, the system was really happy at that temperature. I'm heating it up by adding more. It's like, you're raising it. It's just like raising the concentration. I'm going to shift to try to diminish that. I'm going to shift this way. I'm going to utilize that temperature, that heat energy, and go this way to the left. Okay. So I'm only using one case here, but open up TRO and you can look at the different scenarios. I could say, well, what if temperature were decreased? What if temperature were decreased and it was endothermic? Okay. You're going to figure out whether it's endothermic or exothermic by changing temperature and looking which way it shifts. Okay, so you get to think about that. I'm not going to give any more clues on that, but it's a really interesting way. Instead of telling you whether something is endo or exo, you're going to change the temperature. You can either increase temperature or, like I did playing around with this afternoon, I ramped it up to a really high temperature. And I noticed the shift in equilibrium as denoted by the color. It went from one color to another. I'm like, it's shifting that way as I increase temperature. That will tell me something about this reaction as written. Okay, so we went over that. Was there anything else? I want to just, everybody can see my screen, right? The Chem Collective. Yell if you can't. I can't. Okay, you're going to come on. The instructions are on the sheet. You're going to come under equilibrium, Le Chatelier's principle, and you're going to scroll down to the last one. We're doing cobalt chloride, and you can hit go. And like I said, it gives you this little blank little workbench here. Watch the video. You'll understand how to do this.
Can't see your screen.
See, you're kind of late. I was hoping that. Now, can you see the workbench?
Yes, sir.
Okay, thank you. Okay. So it's not too difficult. I think the first thing is, hey, fill an Erlenmeyer filled with cobalt chloride. So here you have all the solutions that you're going to be using. Here you have glassware. It said Erlenmeyer, so I'm going to go and grab an Erlenmeyer. I don't know. We're putting 25 mils in at the beginning, so I'm just going to, this should be sufficient, right? Then I go back and I want cobalt chloride. I want 25 mils of it. So I choose it. And then I get to, I'm on a Mac here, so it's like, oh, okay. I even forgot what I did today. So I want to transfer that into the flask. So it seems very intuitive. Why don't I just do this, right? And then it comes up with this little thing. Well, how much volume do you want? I'm like, I want 25 mils, right? And then I'm going to pour that. Notice the color. That's the pink color. It's red. I'm hoping nobody's colorblind. If you are, you can email me and we'll work through an alternate way of looking at this lab, because that's going to be an issue if you are colorblind. And every year there is somebody who is colorblind. And usually you have a partner when you're working in the lab to help you. But this one, flying alone, it's going to be cumbersome. So reach out to me. And I apologize for the non-inclusive lesson here. So that's the way you pour that in. And then there it is. There's your reaction flask. And it's ready. And I think the next thing is, hey, go back to your stock room and you're going to add some hydrochloric acid to it, but it says do it 1 mil by 1 mil. So you're going to do these 1 mil volumes. So I poured in and look how the volume changed. Look at how the concentrations are changing. So the concentrations are changing because they're reacting to that perturbation. You're adding chloride to it. So take a look at that reaction. We're upping the concentration of chloride. What do you think is going to happen eventually when we add enough chloride here? Okay, here we are. It was pink, so we were far to the left, right? Everybody can see my document camera?
Yeah.
Spencer. We're adding chloride ion in the form of HCl. We know that HCl tears apart to form hydrogen chloride. That's upping the chloride concentration. What's going to happen to the system at equilibrium, folks?
So wouldn't it shift to the right?
It's going to shift to the right eventually, right?
Yeah.
Yep. Good. And you can do that. I don't know why I'm doing the first experiment for you. I just think it's so nifty. I'm trying to get you excited.
No, you can do the whole experiment for me.
Oh, come on. I'm not going to do it. No, but I'll keep going. So pour, right? Pour 1 mil. Do you notice any color changes? Those who of us can see color changes here. Pour. It's getting a little darker. It's not like a titration here. It's not going to go from pink to blue immediately. You're going to see it kind of get darker, darker, and then a bluish tinge come to it. You can overshoot it like I did today. It doesn't matter. And maybe keep going. I don't know how much I added here. I'm going to go like 40 mils. I've added 40 mils. There's the color change. I'm going to blue. So I know that I've shifted it to the right as predicted. You just utilized Le Chatelier's principle, by the way. That's what I'm looking for. here as a description based on the principle. We've upped the concentration of chloride. It's going to shift to that right-hand side, denoted by that blue color. We're now over on the other side. We've created more of the cobalt chloride complex. We know we're there. We can keep going. One thing to keep in mind, notice this, folks, my temperature is still climbing. Unless you change the temperature and it asks you to change the temperature in one of the steps in the assignment, I'll leave that up to you. It's going to try to get back to 25 degrees here. Let it get back to 25 degrees before you read these concentrations. Okay. While I'm doing that, it's trying to get back to equilibrium. It's going to take a little bit of time here. While you're doing that, I want to go back and just remind you, well, you're going to remind me. There we have a system of at equilibrium. What would be the equilibrium expression? Remember, it's the concentration of the products raised to their stoichiometric coefficients over the concentration of reactants raised to their stoichiometric coefficients.
So wouldn't you write cobalt with the chloride on the product side? Over,
That?
Yeah, over the I don't know how to say that word, but yeah.
Yeah, that other messy thing with the water. Yeah, it's cobalt, hexa, because there's 6 waters, hexahydrate, but it's an ion still. And then what else?
You write chlorine and you raise it to the 4th power.
Excellent, good. You're doing the work for everyone now. How come you didn't include this other product on the top here?
Because you never include a solid or a liquid.
Great. Solids and liquids don't appear in the K expression. You rock. You got it. There we have it. So there's your K expression. After each step, it wants you to calculate the K expression. Do you think at a constant temperature, your K expressions are going to change? It is an equilibrium constant, by the way. So you'll find out. Each time you perturb the system, you're going to get different concentrations here, and you'll see that. But when you go to calculate your K, look what happens. I'll leave that up to you. But I just want to go back to this. We have stopped. My numbers have stopped moving. That's great. I'm going to record these numbers. There's the cobalt hexahydrate. I need that. I need the chloride ion, and I need cobalt in the chloride complex. I need these 3 to go back into that K expression so I could figure it out. Okay. I think that's enough hints here. I think you can figure this out because you guys are more tech savvy than I am with this stuff. And you got through last week's laboratory. Okay, so you're welcome for not having another lab report. You're welcome for it. You'll never have to write another lab report. You do have a poster coming up, but posters are fun. They're kind of like lab reports. They're less writing, more visual stuff. That's coming at the end of the semester of this course, which is mid-April. It's coming fast. The remaining labs are, again, fun and virtual, but there's no more lab reports. There's not even a formal lab report. So there's like data sheets or questions that you'll answer, stuff like that. You still have to do some work, but. I've been chatting for a bit. Thanks for listening. Any questions? You're such a quiet group. I bet you wouldn't be quiet in lab. I bet we'd be having fun on a Tuesday night. All right, you have organic chemistry to look forward to, all of you who are taking organic chemistry this fall. How many people are taking organic chemistry? Give me a thumbs up in the reactions or visual. Cool. All right, you're gonna have fun in lab. All right, over and out. Thanks for listening. I'll post this if you ever want to look at it again, if you forget something. See you guys.
Thank you.
Else.
Thank you.
Thank you.
Thank you.
Welcome.